foundation force you came across in your dynamics of structures. Initial seismic shock. So how long it will take and how, period of vibration as well. We will see a little bit of this a bit later. Okay. Now, for structures built on soft ground, the earth motion at surface is amplified. So soft ground amplifies the earth motion at the surface. The earth motion, structures built on soft ground, earthquake motion at the surface is amplified by the effect of the soft ground. Let me make this a bit bigger. Is amplified by the effect, and the ground will continue to vibrate sometime after the initial shock wave. So the duration of this event is prolonged if we have softer ground. Therefore, in order of suitability for foundations, hard foundations are more desirable than soft foundations. For these reasons, that the amplification of the motion of the earth, because the ground is soft, and also the duration that this event will continue taking place. As the ground becomes softer, this duration also increases. So therefore, in order of suitability for foundations, the harder the foundation ground or the foundation surface where we're placing the building, the better it is. So reducing order of suitability. Reducing order of suitability. Okay, as the ground becomes softer, it becomes less and less suitable for placing buildings, especially the relatively taller buildings that will be subjected to that need to be designed for earthquake occurrences. Now, this standard, at this point, I want to draw another parallel and another maybe difference between this standard and the newer standards that we now have. You notice here that there are 4 broad categorizations. Okay, 4 broad categorizations: igneous and basic rock formations. It's a very broad thing. Then sedimentary and metamorphosed rocks, stiff clay, also is another broad categorization. Then coarse sand and gravel, sandy clay, is another broad categorization. Then fine sands, medium and soft clays, silts, volcanic ash deposits is also another broad categorization. Now, if you think about it, you could have a whole array of possibilities when you talk igneous rock in terms of how hard the rock is. Okay, it's the same thing when you come to sedimentary rocks and metamorphosed rocks. In terms of how hard those rocks are, is a whole array of possibilities. Probably from your geology, you would be able to pick this, or even if you went online and just checked the strength ranges for, say, sedimentary rocks, you find it's a huge variable, etc., etc. And therefore, this standard, in as much as it recognizes that there are these, the hardness of the ground does affect how much force eventually a building will experience and therefore needs to be provided for, is not as refined as what we have in the newer standards. I highlight 2 things that you find as a refinement to this. So the similarity is that this recognition that the type of ground condition does affect the amount of earthquake force. This one is universal. You pick any standard that deals with earthquake forces on buildings, you'll find a similar categorization. You'll find a recognition that as the ground becomes harder, it becomes more suitable, and therefore the building is likely to experience a lesser earthquake force for similar earthquake occurrence. The refinement, what I've seen in the newer standards, one is that now instead of just broadly grouping, say, for example, igneous rock and basic rock, some standards, I think, like the American standard, I have a copy somewhere. Remind me, I'll share with you. That one and this one, I'll share. I have copies. Even the IBC, if you want, I'll share it. In that standard, the hardness of the ground is quantified scientifically by a measurable scientific value. This is shear velocity. So the newer standards will talk about, will do recognize that the hardness of the ground is important, but they go ahead further to one quantify that how hard the rock is by measurements like shear velocity. You find this in the American standard. I'm thinking even the Eurocode, because I've not read it extensively, probably it does take care that it does use this this kind of measure, because it's a more accurate measure for measuring how hard the bearing material is. So this is one. Two, you find that in some instances it is possible to, so you dig. So that's where your ground is, let's say. That's where your ground is. You want to put your building there. You want to put your building there. Okay. Then you do a geotechnical investigation. You dig a borehole here. And you find that maybe, of course, you'll find layers. The ground is, most of the times, is stratified somehow. So you find that maybe loose material. Then you find maybe weathered rock. Then maybe you find another loose material. Then maybe you find later on, further down, you find hard rock. Okay, so sometimes this hard rock is so far down that it does not make economic sense to dig to that level just to be able to place a foundation there. I'll give you an example. There's some buildings we are trying to build somewhere, and of course the design has changed a bit from time to time. But at one point, the client wanted these buildings to be 25 levels, 25 stories. We had done a geotech, dug to about 10 meters, done boreholes to 10 meters below ground, and we had found that initially the design was 20 levels. So when we did this geotech, we found that at around 5 meters below ground, we have some good ground we can put the foundations for these 20-story buildings. Then when the design changed, now the building became taller, so this ground was no longer adequate. So we say, so what is lying below there? And we realized that the good ground is not very thick. It's maybe 4 meters thick, and then it becomes again not very good, and then later on it becomes thicker again. Now this standard that we are looking at does not take care of this occurrence where we're saying, okay, so we want to put our foundation, for example, here, 4 meters below ground. But the good ground is 10 meters. So how do we take care of this? How do we take into account that not very good material between where we want to put the foundation and where we have the solid rock? This standard, and I'm imagining the other older standards of its age also, have this shortcoming that they're not taking care of it. But if you go to the newer standards, I'm certain in the American standard, because I've read a bit of it, you will find that it tells you, for example, if you find you have this kind of material here, and maybe it is also not very strong, but the hard rock is 10 meters or 15 meters below, and you considering to put your foundation here, then this material between where you're putting your foundation and where the hard rock is, you need to take care of it this way. You need to put these factors to help to take care of that amplification. That amplification and the continuity to vibrate, because now it's like you have a solid floor, then you put a mattress, then you're putting a building on top of a mattress. Okay, so these older standards do not take care of that, but the newer standards do take care of it. If you read, you'll find this kind of this kind of refinement. So it's important to note that as we take into consideration these, so we have taken we've mentioned 3 items. There are a few others that are minor that you will refine as you go along once you understand the basics of how we calculate earthquake forces. My intention for this course is to introduce you to how we would pretty much approximate these earthquake forces for relatively not very tall buildings. Later on in our discussions, you realize that this Kenyan standard is limited to buildings of up to 20 stories. Beyond 20 stories, this standard is not adequate. So because in our country, we have the blessing that we get to design pretty taller than 20 stories. Most probably some of you will find the need to design such taller, and therefore this is the starting point, and then you will be able to easily upgrade to any other standard that you need to take into account for. So these are the basic considerations that are almost universal. There are a few refinements, as I've said. Now, there are a few other items that are important. For example, the shape factor of the building, that a regular building, a rectangular building will behave much better in an earthquake than a building that has got a shape of an E or something like that. So this, once you receive this standard, because I'll share it with you, please take time and just read. This standard is a short standard. It's only 25 pages. Just read for your understanding, because the thoughts in this standard are basically universal. Okay, so these considerations you'll read, but I want to now take us to where we calculate the force on the earthquake, the actual force on the earthquake. Sorry. I'm scrolling down. So this is important. We will look at this shortly. So the sections I've skipped, please, when you can, just read through for your better understanding. Now, the earthquake force, generally, is calculated by this very simple equation. F is equal to C times W, where C is the coefficient of earthquake. Sorry, coefficient of earthquake coefficient. And W is the weight of the building. W is the weight of the building. F is the total earthquake force. Total earthquake force on the building. Okay, so this is the simple equation universally that is used to calculate the earthquake forces. The three considerations that we have looked at and a few others, they are usually taken into account when calculating, when determining this coefficient. So let me write here as a note next to this, that this coefficient, this one. This coefficient usually takes into account, good morning. Yeah. Takes into account, this coefficient usually takes into account this coefficient, let's write it properly, and takes into account usage of the building, the type of structure, frame or load bearing, the type of structure, and the ground conditions. Three considerations, broad ones that we have discussed. They are all usually taken into account by that C, coefficient of earthquake force, or simply earthquake coefficient. The total force, this is the total force that the building will feel at the foundation, courtesy of the earth moving. Now, I want to take you back to where we started from in the discussion in this topic. We said that the earthquake force is an inertia force. So the building is static. It doesn't know that the earth is moving. Then suddenly the earth is moving. So the building is still there. So courtesy of that movement, the building is forced to want to move as well. So that force, that total force, is what is referred in this very simple equation as F. Now, the weight of the building is defined depending on the type of building. And this, again, this thought is true across all standards. This thought of defining the weight of the building according to the use of the building is true across all standards for earthquake. Okay. One more thing before we move to look at how we define that. This force here is also referred to as the base shear. If you pick the Euro code, if you pick the American standard now, or the International Building Code, you'll see it will be talking about the base shear. It is the shear, is the force at the base, at the foundation of the building. The shear force is the force that is going across at the foundation of the building. So it's referred to as the base shear in the newer standard. So now I want us to look at how this standard suggests us to calculate the weight of the building. So we go back up here and we look at this section. We look at this section here. Sorry. So this standard suggests three main groups of buildings, and then goes ahead to suggest what we should take as a weight for those buildings when we are calculating earthquake forces. The first group, class A or category A or something, is buildings that are for normal type buildings, domestic offices, etc., etc. The weight of the building is considered to be simply the dead weight. The weight of the building is simply considered to be the dead weight of the building, including walls and partitions. So slab, beam, column, walls, partitions, dead weight of the building. This is what for normal type of buildings like the U block, S block, etc., etc. These are normal type used buildings. It is adequate to consider only the self weight of the building or the dead weight of the building. And why is it like this? When an earthquake occurs, if an earthquake occurs, for example, and I am seated here and on this, and if the earthquake, if the amplitude is big enough, what will happen is that the slab will move with the rest of the building. Probably I will remain where I am with my desk and my chair, because we are not fixed to the building. Okay, this is the thought behind this consideration. Now, in some newer standards, they specify that we take the dead weight of the building for this type of buildings. For example, I think in the Eurocode, if I'm not mistaken, is the dead weight plus 25% of live load. Okay, either 25 or 50%. And you find that this definition of what the weight of the building is, therefore, would vary from one standard to the other. But that it needs to be defined. It is universal that all standards define what they consider to be the weight of the building. So this is the first group of buildings, normal type buildings, domestic, office, etc., etc. To this standard is purely just the dead weight of the building, but to the newer standards, you find that they say the dead weight plus a percentage of the live load as well. Okay. Then the second group of buildings, this is warehouses and storage structures. So you go to industrial area, you find that there are those industrial buildings, maybe with a mezzanine floor or something, and sometimes stuff is put there, as part of storage. The other important storage structure that will be interesting to think about on this category would be for example, parking silo. These parking, elevated parking silos. I think where our campus is, across the road, there is a parking silo across Haile Selassie. There's a parking silo next to the Shell petrol station or something. So when you have storage like that, because that's storage, then or if you have go down and you're putting stuff there, so you would want to. This standard says the weight of the structure will be, or the earthquake weight, the weight to consider would be the dead weight of the building plus 25% of the designated live load. Again, this number of 25% could vary from one standard to another. Maybe some other standard will say 50, 75, 60, depending on their data and what the experience is. And the third type of structure is the kind of structure that we use to store liquids or bulk storage. Bulk storage would be like grain silos, for example. Bulk storage would be something like grain silos. Grain silos. Silos, cement silos, etc. Okay. So these are structures for bulk storage. In this category of structure, if we were designing for earthquake for such a structure, then this standard says the earthquake force should be total to the weight of the building plus the contents. So 100% dead weight and 100% live load as well. So everything that is contained there. Why is this suggested or specified this way? I want to give you an example. So a few years ago, I had the privilege of looking at some grain silos. Some grain silos. So let me just draw here and give you the dimensions roughly so that you can visualize. So these silos were about 30 meters tall. Actually, some were a bit taller. So let's say 33 meters. So 33 meters tall. If you're doing a building floor to floor height of 2.85, 33 divided by 2.85, that's 11 stories, 11 or 12. No, let's say 11. Okay, that's 11 stories. Ghorofa 11. And then the diameter of these silos that I got to look at was 15 meters. Okay, 15 meters. Just you can see that that dimension and visualize it. Now these silos, they were meant to, when loaded to capacity, they were carrying 5,000 metric tons. 5,000 metric tons of grain. Actually maize. But the structure itself, the thickness of the wall, they were reinforced concrete structures. The thickness of the wall here was only 100 millimeters. 100 millimeters is 10 centimeters. It's small amount, small dimension. So, but it's 100 millimeters. It's 15 meters wide in diameter, and then it's 10, 11 stories tall. So it's a huge structure with, when you consider the dead weight of the structure compared to the weight of the contents, the dead weight of the structure is almost negligible. So that's the first example. Let us look at water tanks, for example, because it's liquid, and so consider water tank. Consider, for example, the pressed panel steel tank. We'll talk about this in the other unit for low-rise structures. Don't worry about this. We'll talk about types of tanks. This tank, the wall is these steel tanks that are panels that are bolted. So that steel plate that is folded and bolted is about 2.5 millimeters thick. It's very thin. It's 2.5 millimeters thick. Or if you get very generous, maybe 3. I'm not sure whether I've seen 3. Usually in the range of 2.5. If you get some Mikora, they will even give you maybe 2 or 1.5. I don't know. So it's a very thin element. But then you get a huge tank. You can have easily, let's say 555. You can easily have a tank that carries what? Even 50,000 or 50 cubic meters or 100 cubic meters, or no, huge tanks. But the structure itself is very, very thin. So if we were to consider only the structure, then we would grossly underestimate the earthquake weight of that particular structure. So that's why this category, where we have liquid containing structures or bulk storage structures, this is the thinking why this standard, and most standards the world over, will say that the weight, the earthquake weight, the weight that you use to calculate for earthquake for this kind of buildings should ideally be the weight of the building plus the total weight of the contents. This is the thinking. So now we have said the earthquake force will be calculated by simply calculating a coefficient of earthquake, which will take into consideration mainly the three considerations that we mentioned, and the weight of the building, which is defined according to the use of the building. And I will repeat to say that this use and how the weight is calculated varies from one standard to the other. I've given you an example that in the Eurocode, this category does not allow just the dead weight of the building, but the dead weight of the building plus a percentage of the live load of the building. Okay. I want to pause here and ask if somebody has a question or a comment before we look at one more thing, and then I will stop this class. At that point, I have a meeting from around 9. Any question? Any comment? Great.
Good morning.
Yes, please. Go ahead.
My question is actually there are two. Now, this the factor, the coefficients that we are multiplying the weight of the building with, does it does it have an effect of raising the force? Okay, I'm not in the table, but does it have an effect of raising the force, or is it reducing that force?
Very good question. Very good question. Okay, maybe you could ask the second one as well, so that we try to address both of them.
The second one is on wind loading.
Let's leave. Have we discussed wind? Yes, we have.
Yes, we have.
Okay, so please, you can ask.
It's on. Okay, the shape of a building, I think, affects the behavior of wind around it. Because if you have a building that is cylindrical or circular compared to a building that is rectangular, then the wind will have a different effect on it. How comes we are not considering the shape of the face of the building when we were doing the calculations on the wind?
I think that's also a good question. It's not that we are not considering the shape of the building. There is some things that I intentionally did not mention in class. So, you see, you are a group and your capacities are different. So I need to measure to say what is reasonable for the average student. Because we could go into more details and by doing so lose some, and then we will not have made much progress. And that's why I keep referring you to some other documents and telling you, please, you can look up this one, you can look up this one, because I am trying to instruct to the average student, not the above average student. The shape of a building is absolutely important. And I did mention this at the start of our discussions for wind. I even said, when I was telling you, please go and watch this documentary for the badge in the Arab world, that the shape is so important, but because of the complexity of the wind, we can do all the fancy calculations we need to do, yet if the building is significant, no amount of analysis will be able to fully answer to how the building will behave. And therefore, eventually a building needs to be put in a wind tunnel to just see whether the predictions of how the wind will behave were correct. Okay, and in this documentary, which I sent you to watch, they show this example of their building very well. Initially, that building, the shape was not what they actually put up, and the building was shorter than what they actually put up. But when they took it to the wind tunnel, the response of the building to the prevailing winds was so bad that they had to change the entire form of the building. and therefore you have these parts that are like you have portions, not short, but relatively short portions that are a bit irregular, and that was done to sort of confuse the wind. That was done to confuse the wind, so that instead of forming large vortexes that then would cause the building to sway too much, you form smaller vortexes. So the shape of that building actually breaks down what would have become large vortexes into relatively smaller vortexes that would be less critical to the building. And when they did that, then they did the analysis, and then they took this to the wind tunnel. The building was so much more efficient in confusing the wind and therefore reducing the effect of the wind of the building, that they could add some more floors. And that's how this building wound up becoming much taller. Okay, and I urge you to go and watch that video. And this wind problem, and even this earthquake problem, whatever I'm presenting to you, is a foundational, is to start your thoughts off. So we by no means are pretending to have covered anything that makes us experts in either wind or earthquake. Myself, I am teaching you, and I've done quite a number of buildings, significantly tall, trying to address these requirements. I am not yet an expert with wind or with earthquake. Okay, so this is my thought to Bwana Mutero on these things. And I did mention that the wind problem is really a complex one. Okay, I hope that helps a bit. Any other question? Any other thought? Okay, great. So I want to move us now to look at an example, not example as such, but just look at one table, how this standard approximates or estimates the earthquake force, and then in the next class we will actually do the numbers. We'll put numbers into our building, the hypothetical building that we're doing. I'll start you off, and then you will make the calculation. So to wind up this session, I want us to look at this table. We'll come and do the calculations in the next class, but let's just look at this table for now. So this table gives us an idea of the coefficient of earthquake force that we need to apply for building. Oh, there was another question you asked. Sorry. The question was, do these conditions increase or decrease the earthquake coefficient? Okay. The earthquake coefficient is a number that allows us to approximate the force of earthquake as a small percentage of the total weight of the building. I'll repeat that. Maybe I could even scribble it here. The earthquake coefficient that enables the approximation of the earthquake force as a fraction of the total weight of the building. I'm trying to answer this gentleman's question. So that in itself tells us, maybe not necessarily, but now I'm telling you that it is a small percentage of the total weight of a building. Now, that answers partly your question. Hey, Prof. Now, on your other question, to follow that up. Now, that percentage, that small percentage, that becomes the earthquake force as a fraction of the total weight of the building, is then affected by these three main considerations that we did mention much earlier today. One is the considerations of the usage or the value of the building, such that if the usage is higher, then that value of C will be higher. So for example, the value of C for if all other factors were held constant, the value of C for Class A and Class B building, the value for Class A building will be higher. Then the type of structure. So if a building is, for example, rigid frame, that value of C will be lower than if the building is flexible. Similarly, for this third categorization, that C value, if the building will be sitting on very solid rock, the value will be lower compared to if the building was sitting on, say, coarse sand and gravels or softer material. Okay, so it varies according to these considerations, and maybe we need to look at that in the next session. We'll look that table I wanted to show you. Maybe we need to look at it in the next session. But that is how the value of C varies. But it's a small percentage of the total weight of the building. So if the building is, say, maybe 100 tons, the C value would maybe reduce this, so the earthquake force becomes maybe 2-3 tons or something like that in total. But we'll look at that to detail, I think, in the next session. I want to allow, if somebody else might have a question or a comment before we stop this session, before we close this session. Any other question? Any other comment? Mutero, I hope whatever I've said helps. Just a bit, Charlene, wait a bit. Mutero, are we okay? Does
Yes.
this start to answer your questions?
Yes, we are on the right track.
All right. Charlene, please. Sorry, I can't hear you.
What is the effect of lateral loads? Sorry, what is the effect of lateral loads on basements?
On basements? I'm not sure whether I understand that question.
Okay.
I'm not sure whether I understand that.
Earthquake affects basement of the building because they're already below the ground. Because when we were calculating previously for the wind, I didn't see the consideration of if the story is actually -1, -2. Yeah.
Okay, so now I understand. There's a concept that there's a divide between engineers this side and this side. I wanted to avoid to discuss that with this group, but because you've asked it, I will discuss it once we have calculated this earthquake force. It's not the effect of the earthquake force on the basement that is important. It is the consideration of where the base is, whether it's at the ground level or is at the foundation level, if the foundation level is significantly below the ground level, if we have basements. I'll repeat. The important thought that there is a divide now amongst engineers is not the importance of the earthquake force on the basement, but what is important is the consideration of where the base of the building is when we think earthquakes. That is to say, do we put the base at the ground floor level, or do we consider our base to be, say, if we have two basements, we consider our earthquake base, or the base for calculation of earthquake, we consider it down there. And this one, now that you have asked, we will discuss it in this class. First, let us go through the calculation. Once we have done the calculation, when we come back to this thought, it will be easier for you to make your own opinion and to contribute to this discussion. So that's my suggestion for now. We will discuss it. And if at that point you still have a question after we have discussed it, then we can again ask it. And you need to remind us, let me see, maybe at the end of this coming session, let us see whether we will have discussed enough to be able to make sense of this thought that I'm saying we need to discuss. It's not the importance of the basement, but the importance of where we consider the base of the building in our calculation for earthquake. Any other question? Any other thought? Okay, great. So I think we leave this discussion at this point, and we will pick it up again later on in our next session, and we'll continue. So have a good morning. Thank you.